trapped ions, and my more specific project was building the trap resonator. So first, a little bit of lab background. So in my lab, we use trapped ions to study quantum computing. And I think we should start by answering really what is quantum computing. But we need to understand what a computer is first. So, with a normal computer that we're using right now, you have bits representing 1 or 0. These bits are located within the machine, and they're used to solve different problems. So you can, or tasks really. So it doesn't matter if you're searching the internet or if you're, doing math homework. They're all problems, and those bits are what's used to help solve them. So these bits solve these problems in a linear fashion, which means they'll do one step at a time. Once one is done, they'll move on. So now with a quantum computer, they still have bits located within the machine, and these bits are also used to solve problems. However, the difference is not only do the bits represent 1 and 0, but they can represent these strange values in between. These computers work on different parts of the problems at the same time, which means they're more efficient. So a little analogy is if you have an XY plane, with a normal computer, you have a bit either representing 0 or 1. Those are the two values, and they can represent on or off. But with a quantum computer, you can have these vector values in between. And they're not necessarily 1/2 or 3/4. They're just considered vectors, so it's a little strange to think about. But now let's go back to the lab background. So in the lab, there's a trap used for capturing these ions. And the way we do it is we use lasers and a resonator. So the ions we trap are calcium ions. And you may ask, why calcium ions? Calcium ions look like hydrogen. Why is this good? This is good because hydrogen's energy levels are arranged in a certain way, allowing it to be cooled by laser light. And this means that when we have ions that are looking like hydrogen, they can be cooled too. And when the ions are cooled, they get trapped. So if we look at the periodic chart and we find hydrogen and calcium, when we rip an electron off calcium, it becomes Ca+ and looks like hydrogen. The energy levels look the same, and the laser light can cool it down. And this, in conjunction with the RF from a resonator, which I'll talk about, helps trap them. So how the trap works. So a stream of calcium enters the trap, and then the 375 and 422 nanometer lasers rip an electron off the calcium, turning it into Ca+, which is the ion. And then the 397 nanometer laser is what cools the ion. And then a resonator that is attached to the trap produces an RF signal, and that in conjunction with the cooling laser is what traps the ions. So this is an oversimplified picture of what the trap looks like, where you have the main chamber here with the calcium that flows in, you have the lasers that shine in, and you have the resonator. And that is an actual picture of the trap. So that's the chamber, the resonator's over there, the laser light comes in here, and that's the software we use to run it. So now let's talk about my specific project. So my job was to build the resonator for the ion trap. And the resonator is needed, as I said, because it is the thing that produces the RF signal or voltage to the trap. And it's the only thing that does that. So without the resonator, the calcium ions are unable to be trapped. And you also need that laser, which I mentioned. So resonator parameters. On day 2 of the SHARP program with my mentor, we talked about the parameters that the resonator should have, and they were set for me. So we want a fairly small and compact resonator. If we have a really big resonator, it's not going to fit on the trap that well. And then we want the resonant frequency to be around 40 megahertz. Why 40 megahertz? Well, the calcium ions oscillate at around 4 megahertz, and the ions are most stable when their oscillation frequency is 1/10 the resonant frequency, which means it should be around 40 megahertz. We also want a high Q, or quality factor, aiming for around 80. If the Q is determined by the resistance that the resonator has. So in an ideal situation, there'd be no resistance and the Q would be infinite, but that's not possible. So we want a high Q, and we were aiming around 80-ish. And then we want little reflected power. So power puts in, we don't want to see it come back. We want it to go through. Okay, and we also want a good step up, which means that when we put power in, it'll be a little bit of current, but we want a lot of voltage because the ions care about the voltage. So satisfying the parameters. There is a really big equation that you can sit down and solve, and that'll tell you all the dimensions that your resonator needs to be. But it's more practical, especially if you only have 4 weeks to kind of build a resonator and then test it, and then based on those parameters and what you're getting to make little adjustments. So that's the really big equation. I couldn't even type it out, it was so long. There's lots of different variables that can be changed, and I didn't want to start. So, construction of the resonator parts. To make a resonator, you'll need to make the can, the end caps, the coils, the ground wire, and the circuit board. So the can, end caps, coil, and ground wire, they're all made out of copper. The circuit board too does contain copper, however there is other electrical components on there. Oops. There we go. So, up here we can see different cans. There's all different diameters and lengths. Here is the circuit board. This is the wire we use to wrap around these columns and get different size coils. And some of this wire is really hard to wrap. And then this is the end caps, and there are holes drilled in the ends for assembly, which I'll talk about next. So for the assembly of the resonator, you need to attach the main coil to the inside of the can, along with the ground wire to the inside of the can. And then you need to attach the inducer coil to the bottom end cap. And then you need to attach both end caps to the actual can. And then you attach a circuit board to the very top of it. So, up here we have the circuit board attached to the 2 leads coming out of the resonator. This is the coil and this is the ground wire that's attached. Here it's soldered, whereas here it's screwed. So it's really hard to solder this, so we tried screwing it, which worked. This is the inducer coil, which is in the bottom end cap. And this is kind of like an exploded view of what it looks like. You can see the inducer coil, and then these 2 end caps go on and the wires come out. So the results. The results of my resonator were pretty good considering I only had 4 weeks and I came in here without ever building a resonator before. So my resonator resonates at around 43 megahertz, and it had a Q of about 75. And then it also had about 1.5 reflected power, and it was fairly small, so it fit on the trap pretty nicely. Now if I had more time, I could obviously make little adjustments and make it a lot better. Like the Q and the resonant frequency may be a little lower. If you sand the connections, the Q should go a little higher, and we want to see the reflective power go down a little bit more, even though it is pretty low. So that's my resonator, and this is the resonant frequency. You can see here, this is an oscilloscope, and we use this to measure the frequency. So when we attach it, this wave changes amplitude, and when it's at the greatest amplitude, that's the resonant frequency. And then there it is on the trap. So it's connected right there, chamber's in there, the laser comes in there. That's what it looks like. So a little bit of further research. So now that there's the resonator, we can start trapping a lot of ions, calcium ions with it, and the calcium ions that are trapped will then allow for further research to be done about quantum computing. And hopefully this means that at some point we'll be able to build a quantum computer. I'd like to say I'm not the magical person that built the resonator for the first time. My lab was trapping calcium ions before. I'm just hoping that with my resonator it's a little more efficient, and hopefully they can get more ions so this research can be done faster. Because like I said, it would be really cool if they were able to build a quantum computer with the research that's being done. So this is a picture of the ions being trapped. I got this picture last night. So it really took almost the entire. It did take the entire program to get this to work, but we are getting calcium ions now, which is really exciting. So acknowledgements. I'd like to thank my mentor Dylan, who's sitting back there, and his group for helping me out. They have a much higher level of physics than I do, and they were really patient with me. Obviously, the professors for all their help and work and letting me be in their lab. I'd like to thank Evie, Avi, and Aaron for putting up with me on a day-to-day basis. And the Sharp program in general, because I know there's lots of people behind the scenes that get this done. And then last, my parents, because I do live in Boston, and I would not have been able to have this opportunity if it weren't for them helping me get out here and helping me find living arrangements. So that's pretty much it. Thank you. Are there any questions? Yes?
So earlier you mentioned that you want calcium ions because you're going to switch off and make it look more like hydrogen, but why not the other alkalis, the alkaline metals?
Well, I guess technically we want it to have one valence electron. So with hydrogen, I mean, yeah, I guess it could look like the other ones, but hydrogen is just easy to understand. But yeah, I guess it's something special about hydrogen, how its energy levels are lined up so that the laser light, when it interacts with it, it helps cool it, which traps it.
Is there any reason you do not use hydrogen directly in your experiments?
Yes, because hydrogen by itself is not an ion. We need ions. So if we use calcium and it becomes Ca+, then we have the ions to use. And also, with that picture of the calcium flowing through, if it's not an ion, it's not going to be there's not going to be an interaction. It's going to go through. So once it is an ion, then that RF from the resonator and the laser light will trap it in that place that we can use. Yeah.
That photograph you showed towards the end, you said that's the trapped iron.
Right there?
Yes.
Yeah.
Can you explain a little bit what
I'll
are you
try,
looking at?
and I guess Dylan can correct me if I'm wrong, because I did get this last night, but I believe that these right here are more of the ions, and this was on the computer screen by the camera that we see when the ions go through. So these are more the ions, and I think this is just more noise that's going on. Not all of these things are ions. It's more centered, because I was watching them do it, and when they said it wasn't working, it still kind of looked like this, but there wasn't a concentrated white dot area. So I think those are the ions.
So this is reflection or transmission, scatter light, or what? What is it?
The ions?
What are we looking at? What's the signal?
The signal, I'm not 100%.
So you're looking at is it a sample that you're looking down on, or is it the signals being transmitted through?
Is it light scattered, or how?
No, the camera's looking down through the chamber at it.
I see.
Yeah.
And so this is scatter light.
Yes.
Of one light.
From the calcium.
Okay.
Yeah.
What advantage would a quantum computer have over a regular computer?
Okay, so kind of like I said before, with a quantum computer, it can work on multiple parts of a problem at the same time, whereas with a normal computer, normal computers are very complicated. I'm not trying to say that they're not good, they're very good, but they work on things in a linear fashion, so they do one thing at a time, whereas a quantum computer can do multiple things at the same time. So I guess kind of a good example is like factoring, where like with a normal computer, if it tries to factor something, it's like looking at each individual number and putting it in, whereas a quantum computer can look at all numbers and instantly know if they'll go in or not. So you can kind of think of a quantum computer as kind of like a tree with different branches going in different areas, and it's all coming back at the same time and analyzing information that way. Does that answer your question?
Yeah.
Yes, Aaron.
What does calcium have to do with quantum computing?
Well, I think the ions, we're using nanowires too, or my lab's using nanowires to see if they can take these ions and get the information to go across them, like those ones and zeros. They kind of represent the switches that are like on or off. And then because it is the quantum study, they can be in those weird stages where they're technically in both positions at the same time. I still don't even really understand it that much. But
I don't think anybody really does.
No, it's very mind-blowing. But yeah, so I think those ions, they're just using them to see if they can get the information to flow across the nanowires and see if they can get the information to move like that. Yes?
Would it be kind of like correlated to like the half spins, like up or down, where you don't know where they are, and then?
Yeah, I guess you could look at it like that. Yeah. I mean, I haven't taken like calculus or high-level math yet, so when he was explaining vectors to me, it was a little confusing. But he said, Dylan said that you can think of it as kind of like vectors. So it's not 1/2; it's some weird value that's just in between 0 and 1, or on and off. It's like both on and off at the same time. I don't know, it's weird. I built the resonator. That's what I did. Resonator questions. I do.